Hello guys, good evening. My name is Danny Tumijan and I'll be going over the test for 2018. And after that, I'll be going over a couple questions from the ACS booklet just for some practice for the multiple choice that we're going to have. Because Dr. Bean said that it's going to be similar to what you're going to see in the ACS. So let's start with the nomenclature. Starting with this one. So the first step you always want to do is you want to find the longest chain possible. So using that number one rule, most important rule, I'm going to have different options and different colors. So the first option is going to be 1, 2, 3, 4, 5, 6, 7, 8. The second option is going to be in the pink color. 1, 2, 1, 2, 3, 4, 5, 6, 7, and 8. And the third option, I'm going to do it using the purple color. So 1, 2, 3, 4, 5, 6, 7, and 8. Right, those are the three options for the longest chain possible. Now, knowing that, how do we decide which one is going to be the one that I'm going to be using? So for that, you have to look at the number of subs. The higher the number of subs is the one that you choose. So if we look at the red one, we have one sub for the red one. We have the second sub right here, and then we have the third sub right here. So it has 3 subs. Now if we look for the purple one, it has 1, 2, 3, 4, 5, and 6. Right, all of these are subs. So that means we have 6 subs. Subs is like substituents. And then the last thing that we have to look at is the pink. Now looking at the pink, we have... Actually, let me just erase these really quick. So looking at the pink, we have 1, 2, 3, 4, and then 5 substituents. So from that, we know that we have to choose the purple one because it has the highest amount of substituents. So let's erase everything that is not the purple. Alright, so we know it's going to be the purple one. Let's erase that. Now, how I like to do it from here on is working with the system. So I start by putting the subs. And then I'll have the root. And lastly, if I have any stereo to look at. So looking at subs, I know that I have 2 methyl on carbon number 2, and that I have a methyl on carbon number 7, right? So that tells us it's gonna be a 2,2,7 trimethyl. 2,2,7 trimethyl. The second thing is, on carbon number 5, we have a cyclopentyl. So 5 cyclopentyl. On carbon number 3 and carbon number 6, we have ethyls. So that's going to be 3,6-diethyl. And then now we look at the root. So for the root, it's 8 carbons, so that means it's octan. And then lastly, in this case, there's no stereo, so I'll just put not available. Now, when I want to put the name together to form the final name of the molecule, what you have to consider is always putting it in alphabetical order. So what I mean by that is, for instance, the M and the E, which one would win? The ethyl, right? Because E is alphabetically before the M. Now, there are a couple of exceptions that we have to discuss. When you're talking about, when you have like trimethyl or dimethyl, the T and the D don't count toward alphabetical order. However, there are only 3 that do count, and those 3 are N, I, and C. So neo, iso, and cyclo. In other words, it's like Nick. Just remember those. Those count toward alphabetical order. So these count for alphabetical order. For alphabetical order. So now we want to put the whole thing together. The first thing first is we have to compare the C, M, and then E. So we know C is the first one that in the alphabetical order in comparison to those three. So it's going to be 5-cyclo, pentyl. Then we have ethyl versus methyl. It's going to be the ethyl, so 3,6-diethyl. And then we're going to have lastly 2,2,7-triethyl. And then I do have space. And then lastly, the root of the name of the root, so octane. So that's the whole name. Alright, so now moving on. Again, I do the same thing. I'll start with number of subs. I'll separate them, root and stereo. In this case, we first have to figure out which one is going to be the longest. So if I look at this one, what I usually like to do about these, the linear chain like this substituent and it's like condensed, because like if you haven't done lots of practice, a good way is to just draw it out so you can see it easier. So CH2, CH2, CH, CH3, C, CH3, CH3, CH3. Right, this is the same thing as this thing. Now we gotta decide which one is the longest chain. So if we take this linear chain as our longest, then it's gonna be 1, 2, 3, 4, and 5. But we also have a cyclohexane, 1, 2, 3, 4, 5, and 6. And here it's a CH2 3 times, so 4 carbons here. So it's just 4 carbons. So the longest one is the 6-cyclohexane. Now, when you're looking at these, remember guys, you cannot just go from like 1, 2, 3, 4, 5, 6, 7. You can never have like start numbering when you're coming to nomenclature. You cannot start numbering the linear chain and then move on to the cyclo. You have to always have them separated from each other. So now that we know that, our longest chain is gonna be the cyclohexane in the middle. But now you gotta decide how you're gonna number it. Is it gonna be 1, 2, 3, 4, 5, and then 6, or is it gonna be 1 from this side, 2, 3, and 4? So you gotta decide if this chain is on the 1 or this chain is on carbon number 1. And how you do that, remember when you have two like on the same numbers, the only way to like figure out which one's gonna be number 1, which one's gonna be number 4, you have to write out the name, and then depending on alphabetical order, I add them. So I know that this right here, this chain, the 4 carbon chain, is gonna be a butyl. So I know that this is going to be butyl. On the other side, if I look at this one right here, I know that the main chain is going to be the 5 carbon. Also, you cannot when you're counting the subs, you always want to start counting from the chain towards the main chain. So like I always start counting from here, 1, 2, 3, 4, and 5. You never count from the other side, even though I'm going to have less of that. So if I count from this side, from the pink side, I'm going to have 1, 2, 3, 4, and 5. If I count from the pink side, I have the subs on 2, 2, and 3. Even though the number of subs is bigger from the other side, I have to start counting from where the main chain starts, right? Just keep that in mind too. I know for nomenclature there's lots of rules, but if you practice it enough, it'll become like natural. Now, when we're looking at this, we know that the main chain is going to be a pentyl, right? So pentyl. And then I know that on carbon number 3 and on carbon number 4 there are methyls. There's 1, 2, 3, and 4 methyls. I mean 1, 2, and 3 methyls. So that will make it a trimethyl. So we have 3, 4, 4, tri. Let me just move that a little bit. Trimethyl pentyl. And all of that is the name of the sub. So now you gotta decide between a butyl with a B or methyl with an M. So butyl will win, so that will give us the red number, which 1 is on butyl. So it's gonna be 1 butyl, and then 4, 3, 4, 4 trimethyl pentyl. Now for the root, we're gonna have cyclohexane, as we said. So cyclohexane. And for stereo, you can see here that this one is pointing up and this one is pointing down. So that will be trans. Now when you're putting the nomenclature together, remember that when there is stereo, it always comes first. So it's gonna be trans, even before the number before everything. 1 butyl, 4, 3, 4, 4 trimethyl pentyl, and then it's going to end up with a cyclohexane. You shouldn't have like naming on 2 lines, but I just did not have any more space, so I'm just going to put the line here. Also, another thing that I would like to mention is when you have like when you put like dashes, you only put dashes between numbers and letters. You see how I have it right here? Now when it comes to number C, it's the opposite, right? And this is why you guys should, like, you have to memorize the common names, because if you don't know the common names, then you can't solve this question. So isopropyl is gonna look something like this. I would always remember when I look at iso, I remember there's a Y somewhere. So that's isopropyl. And then for isopentyl, I'm gonna have 1, 2, 3, and then 4 and 5. 1, 2, 3, 4, 5. Right? So you see how I have the Y? That's a quick way to remember it. Alright, so when you want to draw the whole thing, you start by you do the exact opposite of what we did before. So it starts with a decane. That's the root, because we always put the root at the end of the name. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now let's number it. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now on carbon number 4 we have an isopropyl. So carbon number 4, we have an isopropyl. On carbon number 5 we have an isopentyl. I'm gonna erase the numbers because it's gonna be hard to draw. We have an isopentyl. So 1, 2, 3, and then a Y. And then on carbon number 3 we'll have an ethyl. So now let's go backward and check on our work. So 3 ethyl. So on carbon 3 we have an ethyl. On carbon number 5, 1, 2, 3, 4, 5. Right here we have 1, 2, 3, 4, 5. We have an isopentyl. And then on carbon number 4, which is right here, we have an isopropyl. So 1, 2, and then 3. So everything is correct. Always, when you're doing this, always remember to go back and check your work, right? Alright, so now going to number 2. When you're doing those problems, I would like to mention, I was talking to Dr. Bean, and she's telling me that last year, when the students had multiple choice, they was confused between like lowest and highest. Just make sure you read the problem correctly, and like when you have signs, make sure you have them like figure out, like, remember which side is bigger, right? Don't confuse these. And especially in these problems, a lot of people, because they do so many old practices, they come to the test and they like memorize that one is lowest always, but she can flip them sometimes. So just make sure you don't confuse and lose like some stupid points on that. And also another thing is make sure you read the question, because if you don't read the question, I don't know, you can't get the question wrong. Because what happens is lots of people will be like doing 20 old tests and they're like, they get to the point where like, oh, they see this problem, immediately they solve it, but they just don't read the question. So this number 2 is place the compounds below in order of increasing melting point. So melting point and boiling point are practically the same, but there's only one thing that distinguishes these two. In melting point, when the branching increases, sorry about that. When branching increases, the melting point will increase. If you remember, in boiling point, it's actually the opposite. When you're talking about boiling point, when branching increases, the boiling point will decrease. And the reason why is when you have melting point and you have branching, it will let the molecule stack in a better position, making the melting point harder to reach. However, in boiling point, when branching occurs, what happens is it's harder to have LDF with other molecules because they're so crammed in here. And this is what defines boiling point, is intermolecular forces. Even melting point, it's defined also by intermolecular forces. But in boiling point, when you have branching, there is no more LDF. There's no more LDF. There is LDF, but it's a little bit weaker. For the people who don't know what LDF is London dispersion force that happens between hydrogen and the carbon. So this is why that phenomenon happens. Now, I don't know if you're supposed to know that. I'm pretty sure you do, especially for multiple choice. She can like ask you like concept questions more than like just like solving or like practical questions. So anyways, looking at those three problems, we can see that the middle molecule has 1, 2, 3, and 4 branches compared to the first one, which has 2 branches. This one has 1, 2, and 3 branches. So 2 branches. 1, 2, 3, 4. We said 4 branches. And then for the last one, we have 3 branches. So based on what we said, that when there's branching, it increases melting point. This tells us that the middle one will have the highest melting point compared to the last one, which has in between, which is 2, and then the least one is going to be 2 branches. So last thing is place the compounds in order of increasing bond dissociation energy for the indicated bond. So when we're talking about bond dissociation energy, we're talking, in this case, they want us to remove the bond with the hydrogen right here. So when we lose a bond, we're gonna have a radical form. Radical, and then another radical. And when it comes to radicals, you gotta remember that the stability is tertiary radical. Radical is the highest compared to the secondary radical compared to the primary radical. Now, if we look at this radical, the first one, it has 3 branches, meaning it's a tertiary radical. This one is a secondary radical. And then for the first one, it's a primary radical. Now, when we're asked about the energy or bond dissociation energy, so we know that the primary radical is the least stable. If it's the least stable, this means it requires the lowest which means it requires the highest amount of energy. So this one will be 3, then this one will be 2, and then this one will be 1. So again, remember, when we're talking about the least stable, we'll have the highest bond dissociation energy compared to the tertiary. Another thing that I wanted to mention, but I forgot. Oh yeah, when you're solving the test, remember to like how when I solved my test, when I took the test or go on, I always like wrote the rules next to it, like just so I remember them and like keep track of everything, because you can go back and then you'll be going through the problem and then you see what your notes, you'll figure out if you did like a small mistake or something. So I think just taking notes even on the test is useful. So now looking at number 4, she's asking us consider the solubility of NH4Cl in each of the solvents. Place the solvents in increasing order of solubility of the compound in each. So the first thing that you gotta consider is NH4Cl. We know that NH4Cl is an ionic compound, right? Because it's an H4 plus Cl minus. And we also know that ionic compounds are soluble in water-soluble solvents. So knowing that, when we're talking about water-soluble solvents, we're talking something that has hydrogen. The more that has hydrogen bonding, the better. So anything that has OH or like NH or NH2 or anything like that, right? So now that we know that, the first thing that you notice out of those 3 is that the only one that has hydrogen bonding is the OH right here. This one is the only one with the hydrogen bonding. Now some people will consider this one as having hydrogen bonding, but actually this one does not have hydrogen bonding. What it has though, it has dipole-dipole. And dipole-dipole does create intermolecular forces, but it's a little bit weaker than hydrogen bonding. So knowing that, we know that the one with the hydrogen bonding is going to be the most soluble, and then the next one that's going to be the second most soluble is going to be the one with the dipole-dipole. And then lastly, this one is just this one is just a bunch of carbons and hydrogen. That doesn't it's not soluble in water. However, it's fat soluble. So it's soluble in like non-water based solvents. So this one will be the least soluble with taking number 1. So number 5, draw a structural isomer resulting from the monobromination of the compound shown below. You will be penalized for duplicate or incorrect structures. So when we're talking about monobromination, is you remove 1 hydrogen and then you convert it to a bromine. So what she wants us to do here is to find all the isomers for having 1 bromination, not the isomers, but well, it is isomer, but like monobromination, it can occur on different carbons. So what she wants you to do is you want to try to find the unique hydrogens on this molecule. I just want to give an example before we jump into this one. If we have like a molecule like this, in this case, you can see that the right side, if I split it in the middle, the right side and the left side are the same. So this tells me if I want to tell that these hydrogen on this side are going to be the same hydrogen on this side. So these hydrogen are the same. So like if I want to put letters on them, I'm going to have A, and this tells that this one's going to be also A, and A, B, and this one is also a unique hydrogen in the middle that makes it C. And every letter will have a different bromine, which is a different structure, right? It's a different isomer, not a different structure. They all have the same compound, but they have different isomers. Now, this is just a side note on the side because I just want to point it out. So let's look at this molecule here. If I try to break in half, it's not a mirror image. So this tells us these carbons on this side are different than these carbons, or hydrogen, because we're looking at the unique hydrogens in this case. So first of all, we know that this hydrogen, this hydrogen, this hydrogen are unique. Also, I mentioned I didn't talk anything about this carbon because this carbon right here does does not have any hydrogens, right? So I cannot have no monobromination on this carbon. No monobromination on this carbon. This carbon is also different, so that's B. This hydrogen is different, so that's C, D. There is no hydrogen on this one, so that won't let me have a monobromination on it. And then I'm gonna have E, E, and then E. And this carbon right here is also a unique hydrogen. The hydrogen on this carbon is a unique hydrogen, so that will makes it F. And now what I do when it comes to monobromination is that I just want to add a bromine on every different letter carbon. So now let's draw it out. We're gonna have so the first one is gonna be on the BR. The first one's gonna be on the A carbon, so that's the BR here. Next, we're gonna have on the B. Then let's put one on the C. Then we're gonna place one on the D carbon, so that's gonna go right here. And then lastly, we have one on the E. Actually, not lastly, we still have the F. So E, we're gonna have a BR right here. And then lastly, we have the F. And then we have a BR right here. So let's go back and check our work. We know that on the carbon A, we put one. On carbon number A, we put one. On carbon number B, we put one. On carbon C, we put a BR. On carbon D, we put one. And then on carbon E, we put one. And then finally on carbon F. I just wanted to show this thing because how it can have a similarity and it can be mirror image in the middle. I know you guys are not gonna have to draw them out. She might have a question where oh, how many isomers are for this compound? Something like that. And then you have to draw them to be able to tell, right? Next question is, rank the following anions in order of increasing basicity. So a quick thing to remember from basicity is that the more stable the base is, this means it's the weaker base, and vice versa. So the least stable base is going to be the stronger base. And for acids, it's also the opposite, so it's going to be more stable. Acid is going to be the stronger acid. And the weaker acid, or the less stable actually, the less stable acid is going to be the weaker acid. So now looking at those three compounds that we have in front of us with the nan on them, we can notice that, actually let me move these a little bit out of the way so I can draw. So for the first one, we can see that there is resonance on both sides. So this negative charge can go over here and pull those pi electrons into the carbon and form a lone pair. And it can go also over here and form a lone pair. So if I follow the blue arrow, I'm going to have this molecule. And I'm going to have a negative charge right here. And if I go with the red one, I'm going to have a lone pair right here. So those are the two resonance structures. For the second compound, there's only one resonance structure with these moving here, the pi electron forming the lone pair. So that would be the lone pair. And for the last one, this compound, there is no resonance. No resonance. And you also guys have to remember that resonance, when you have more resonance, This means there is more delocalization of the charge, delocalization of the charge. And then finally, that means it's a more stable compound, more stable. Alright, so now that we know that the first compound has the most amount of resonance. It has 2 resonance. This means it has the most amount of delocalization of charge, which means it's the most stable base, which means the weaker base. I know it's kind of weird how it's like it's the opposite, so more stable base is the weaker base. Just make sure you know it. So that will makes it the weakest base, which means it's going to be number 1. And for comparing the second compound and the third compound, you can see that the third compound has no resonance, which means there is no delocalization of the charge compared to the second one, which has at least 1 delocalization. So the second one is more stable, meaning it's weaker than the third one. So the second one will be number 2, and then the last one will be number 3. So number 7, predict the product that would result from an acid-base reaction between the compounds below and place the arrows in the boxes provided. Indicate the direction of the equilibrium by placing an arrow in the box. So a couple of things that you guys should remember here. Always when you have this type of question, acid-base, always remember that acid is a proton donor, or a hydrogen, same thing, proton donor. And then the base is a proton acceptor. Knowing that, looking at this molecule, we know that this one does not have a hydrogen, and this one can lose a hydrogen. So immediately, what you guys want to do is, when you have something that is negatively charged, it's going to gain a hydrogen. So CH3, C double bond O, SH, and on the other side we're going to have an OH minus and A plus. The function of the sodium here is just to stabilize the negative, right? You don't want to have just a negative in the molecule. In the solution. So knowing that, we know that this compound accepted a hydrogen, so it accepted a hydrogen, so plus H, and this one lost a hydrogen, minus H. So based on the definition that I said before, we know that the acids are proton donor. So I know that the H2O acts as my acid here. And that the CH3C double bond O S is going to be my base. And then remember from Gen Chem, the base becomes the conjugate acid. I'm going to erase this now because I need some space. So conjugate acid. And this will become my conjugate base. Now, at this point, we almost figure everything. We just need to figure out the equilibrium. For us to be able to figure out the equilibrium, we have to know which one is a strong acid and which one is going to act as a strong, and which one is going to act as a weak acid. So what you do here always is you compare the anions. If you look at this anion and this anion, the first thing that you notice is that this anion, number 1 and 2. So anion 1, it has a resonance structure. So let me draw it out right here. So CH3, C double bond O, S minus. So the resonance structure for this compound is going to be the negative charge can form a pi bond, and the pi bond on the oxygen will form a lone pair on the oxygen. And then what we're going to end up with is a CH3, CO minus, and then S. Compared to the OH minus, so anion number 2, it does not have, so there is no resonance here. No resonance. And remember what I mentioned before about resonance. The more resonance I have, the more delocalization of charge I have. The more the delocalization of the charge I have, the more stable the compound is. So I know that this base is the more stable. Also, remember what I said about bases. So if the base is more stable, this means this is the weaker base, and this is the weaker acid. This will make this the stronger base and the stronger acid. So, and also you guys have to remember that the equilibrium always rises from strong to weak. So it's gonna go this way. And the equilibrium from strong to weak is from like Gen Chem, I think. And that's pretty much it. And in organic chemistry, you always have the strong acid on the same strong base on the same side, and the weak acid weak base on the same side, for you to be able to draw the equilibrium and stuff. Like, I've never seen in her old test or her like practice questions in the class that she never done like a strong acid weak base. Alright, so number 8. For the structure given below, draw the important resonance contributors, circle the major contributor, and draw the hybrid in the box provided. So for this molecule, you're gonna follow the negative charge. And when I was teaching some students, I've noticed that some people will go from like negative to positive, but this doesn't happen in resonance. You always have like negative everywhere. You're never gonna go from a negative to a positive. It's always consistent, negative, right? You're never gonna like gain an electron or lose an electron out of nowhere, right? You need a reaction, and what we're doing here is not a reaction. It's just the movement of the electrons in the pi bonds and the lone pairs. So the first resonance that we can see is that this negative charge can form a pi bond right here, and this pi bond will form a lone pair on the carbon. So that will cause us to have an H here, a lone pair on this carbon, a pi bond here, double oxygen. That's pretty much it for this one, right? The next step is this lone pair. Oh, also I should mention that you can either pull the arrow from the negative charge, or you can circle the lone pair and then push the arrow. It does not matter which one's which. But just make sure to draw the arrows, because some people will forget to draw the arrows, and that's like -2 on each one. So just make sure you draw the arrows. Well, now because multiple choice, it's different. So the next structure is going to be this lone pair can form a double bond, and this pi bond will form a lone pair on the nitrogen. And we're going to end up with a structure like that. Double bond and hydrogen. There's a lone pair on the nitrogen, and then it's negatively charged. Now on the other there's more also resonance structures. So what happens is that this negative charge, or this lone pair, is going to go and form a pi bond, and the pi bond on the oxygen is going to go back up to the oxygen. So now we're going to end up with a compound like that. Negative charge on the oxygen, and H, and that's pretty much it. Now you gotta decide which one is gonna be the more stable, or which one is the major contributor, so the most stable one. And remember, when we're talking about like negative charge, you always gotta think about electronegativity. And when you think about electronegativity, you have to remember the trend on the periodic table, which looks something like this. So this is the periodic table. The electronegativity increases this way to the right, and it increases up. So electronegativity increases this way and this way. So up and to the right. Knowing that, we know that oxygen. So we have nitrogen and then oxygen. We know that oxygen. Actually, I have a periodic table right there. So we know that the oxygen is more to the right of the nitrogen, making it the more electronegative compound. So in other words, what I'm trying to say is the electronegativity increases from the bottom left to the top right. Right. So, knowing that, the negative charge that is on the most electronegative one is going to be this compound right here. So I circled this one, and then lastly they told us to draw the hybrid, and the hybrid would look something like this. We form the NH here, and then you have the oxygen. And now every single double bond that I have moved or lone pair is going to convert to dashes. So you're going to end up with something like that. And then for the negative charges, they're just going to be partial negative. So we know that the partial negative how are you going to draw the partial negative? You don't have to draw on every single carb or every single atom that you had a negative charge on. What you do is you just draw it on the oxygen and on the nitrogen. And then what you're saying here that then the partial negative is distributed between all of that. Right, actually let me use the highlighter for this. So you're saying is that the negative charge is distributed between all of that, or the partial negative charge. Alright, next up is number 9. Consider the structure below and answer the following question. Write the hybridization of each atom indicated in arrow in the box provided. So when we're talking about hybridization, how Dr. Bean explains it is, remember that you have the number of atoms connected plus the number of lone pair, and depending on what this number is, so let's pretend this number is 4, then you know it's an sp3. If the number is 3, you know it's an sp2, and if the number is 2, it's going to be sp, and so on. And yeah, so looking at carbon number C with the arrow here, we know that it is connected to one carbon and another carbon right here and nothing else, so it has 2, meaning it is sp. But remember, when you're doing hybridization, there's something that is really important, is that you have to consider resonance too. So like resonance is going to play a big part of organic chemistry. I'm pretty sure Dr. Bean emphasized that. So what happens here is you see this positive charge right here. This means there is a resonance somewhere that can happen. Not always, but in this case there will be, right? So this nitrogen has a lone pair that can come down and form a resonance right here, and this pi bond is going to go back to the oxygen. So you're going to have a CH2, double bond CH, a C, triple bond C, CH2, double bond N, H, CH3. Now this nitrogen right here is going to now become positively charged. And for the, oh, my bad. I think I'm missing a carbon. Yeah, I'm missing a carbon. Let me just move these a little bit up. So C triple bond, CH2, C double bond now, nitrogen, and then CH3. And then for this one, now we have a single bond to the oxygen, but now the oxygen has 2 lone pairs with the hydrogen, and then the positive charge is now going to be on the nitrogen. So now let's compare these two compounds. So let's look at the carbons. It's the same carbons again. So we know that this carbon right here is going to stay the same. So for both of them, it's going to be sp. For the oxygen, right here, we have 1, 2, and then 3. So that's an sp2 hybridized carbon. I mean oxygen. But if we look here, 1, 2, 3, 4, then we know it's an sp3 hybridized oxygen. And for the nitrogen, same thing. This nitrogen right here is going to be connected to the hydrogen, so 1, 2, 3, and 4. So that's sp3 hybridized. But in this resonance structure that we drew, this nitrogen is going to be 1, 2, 3. It's going to be sp2 hybridized. So when you're trying to do the hybridization and you have resonance, you always try to choose the lowest hybridization number. So now that we know that the oxygen here is sp2 and sp3, so the sp2 will always win. Same thing for the nitrogen. We have sp3 and we have another sp2. We know automatically that the sp2 is the one that's going to be the major one. So you always choose the lower hybridization number. What is the CC-CD and CEB bond angle? When you're asked this question, you always want to look at the angle that's formed by the metal carbon, right? So knowing that, if we look at the CD right here, we know that CD is going to be 1, 2, 3, 4. So it's connected to 4 molecules, so that's sp3. We know that let's just do all of them. So CC, we know that CC is going to be sp as we calculated before. Carbon D is sp3, and then carbon E is going to be 1, 2, 3, so that's an sp2. So as I said before, we have to look at the middle carbon, so it's sp3, and we have to memorize it from Gen Chem. sp3 is 109.5 degrees. That's it. The most three that you're gonna be asking in organic chemistry are sp3 for the angles, sp2 and sp. sp3 is gonna be 109.5. sp2 is gonna be 120, and then sp is gonna be 180 degrees, degrees, and degrees. Those are the most common three that you're gonna get asked in organic chemistry. Actually, you're only gonna be asked on this test. You're not gonna see it further on. So then it asks us the sigma bond between the Ca and Cb is formed by the overlap of what types of orbitals? Be specific. Ca and Cb. So if we go back and look at Ca and Cb, this carbon right here is 1, 2, so it's connected to one carbon, and then there's a hydrogen, and then another carbon, so we know it's sp3, and then B, we know it's connected to two molecule, making it, or two atoms, making it just sp. So the overlap of the orbital sp3 and sp. 1, 2, 3. Oh, my bad. This is sp2, not sp3. Now looking at it, because again it's connected to 1, 2, and then 3, so that's sp2. Alright, moving on to number 10. Arrange the Newman projection below in order of increasing strain energy, lowest energy to highest energy. So, looking at those Newman projection, we remember in class that Dr. Bean said that when you have an eclipsed, I can't spell eclipsed. It's gonna be the most unstable, right? Most unstable. Meaning that this one is the one that has the highest energy. So highest energy. So what I mean by eclipsed is, it's like the compounds are gonna be like near each other or above each other. So there's fully eclipsed and there is partially eclipsed or eclipsed. So if you look at the middle one, this one is not fully eclipsed. If it was fully eclipsed, then you'll have one exactly above the other one. Like they're like, you cannot see the difference. And this one has even more than anything else. So looking at this one, we know that there is a ethyl next to a 1-methyl ethyl, right? So if you look at the middle one, it's the only one that is eclipsed compared to the other one where it's called Gajuan or something like that. I don't know just how to pronounce it, but do you see how there's like distance between them? So immediately that tells us that the middle one is the one with the highest energy. Now comparing the first one and the last one, you have to compare what kind of molecule are next to what. So if you look at this one, there's a CH3 next to this big molecule, I'm going to call it propyl, the 3 carbon. There's an ethyl here, and then there's a methyl. But if we look here, there's a methyl next to a methyl, next to a ethyl, and then next to a propyl. So if you see something here, that this propyl is next to a hydrogen from one side, next to a methyl from one side. But this propyl right here is next to an ethyl and a methyl from both sides. So this tells us that this one is less steric, meaning that this one is the one with the least amount of energy, and this one has the second highest amount of energy, so that will take number 2. Alright guys, so for number 11, she's asking us to draw the more stable chair conformation of for each of the substituent cyclohexanes shown below. So before I start drawing this, we have to keep a couple things in mind while doing this. The first thing that you guys keep in mind, that when we have wedges, it's always up, and when there's dashes, it's down. Now you can switch these, but stay consistent when you're doing that. So you can't just have wedges down and dashes up, but make sure you're consistent. That's what matters. Alright guys, so I noticed that in the first, this is an edited part, I think I want to talk more about the chair confirmation because I realize that's a good opportunity that Dr. Bean can ask multiple choice questions about it. It can be confusing. So what I'm gonna do here, I'm gonna go over the different conformation of the cyclohexane, and I'm gonna rank them from the least stable to the most stable, or the one with the lowest energy to the one with the highest energy, which is the same thing, right? So the different conformations that we have for cyclohexanes are the chair conformation, we have the twisted conformation, we have the boat conformation, and then we have the half chair. And I'm gonna put with number 4 being the one with the least energy, and then number 1 with the highest energy. Highest energy meaning is gonna be the least stable, so least stable. And then number 4 is gonna be the most stable. So we all know that the chair conformation is going to be the one that is most stable. So that's why I'm gonna give the chair conformation number 4. Then the twisted is gonna be this one after the chair conformation, so that's gonna take number 3. And then boat is gonna be the second one, and then the least stable is the one that's gonna be the half chair. So if I want to draw the graph for this one, like the graph of different energies, it's gonna look something like this, just like a wave. So it's gonna go, this is the lowest energy. Those have to be on the same height, but my drawing is not that good, so let me raise this one a little bit. So let's assume these two are the same height, right? This peak and this peak are the same height. So the one that's gonna have the highest energy is gonna be the half chair. So giving those two peaks number 1, we know that the chair conformation is gonna be the most stable, meaning this one is gonna be the least energy. So that's 4 and 4. And this here is the potential energy, right? And then the boat conformation is gonna be right here, and then the twisted are gonna be right here. Twisted is gonna be number 3, so that goes right here. So she can give you a what's it called, a chart, and then gives you the numbers and then where each one will go, and then you just have to match them to it, right? I think that's that's a question that she might actually ask, and if she doesn't give you the names, you should guys also know how they look. So we know the chair conformation looks something like this. The twisted is, it's hard to draw it, but that's number 4. Number 3 is gonna look something like this. Oh, let's do that. It's gonna look something like this. And then you have the boat. And then lastly, you would have the half chair, which looks something, it's gonna be hard to draw it, but so you see how it's like half a chair, so like there's the back, but there's not front of the chair, so that's like a half chair. So yeah, those are the conformations. So that's the boat, and then this is the half chair. Now, another thing that I want to talk about is why, like as we'll mention later on, I'll mention like you don't want to have groups on the axial, and the reason why is because you don't want to have a 1,3 diaxial strain. So what that is so let me just draw the chair conformation here. So let's pretend we have a methyl right here, a CH3, right? And then, so on that's carbon number 1, that's carbon number 2, and that's carbon number 3. And from the other side, it's gonna be, this is carbon number 1, this is number 2, and this is number 3. And when you have another let's pretend even hydrogen here, right? There's strain between those hydrogen, right? And even will be worse if we have like a methyl or an ethyl or anything. And that's why you don't want to have groups on axials in general. So always try to avoid having groups or big groups on axial compared to equatorial. So looking at this, we know that wedges is going to be up. So this is up. And then dashes is going to be down. How I like to solve it is by numbering them. So make sure you number everything. So 1, 2, 3, 4, 5, and then 6. In this problem, it doesn't matter how you start numbering because we're not dealing with nomenclature. We're just dealing with like just to keep track of where everything goes. So knowing that, we're gonna have number 1, 2, 3, 4, 5, and then 6. So the third butyl is pointing up, and so we're gonna point it up here. So that's the third butyl. And then there's the hydrogen. I like to draw the hydrogen just to show which one's gonna be the equatorial and which one's gonna be the axial. The methyl is up on carbon number 2. And then there's the hydrogen. And then on carbon number 5, we know the CH3 is gonna be pointing down. So that's the CH3 right here. Pointing down, so the hydrogen is pointing up. So that's the first conformation. So now if I flip this around and I draw the second chair conformation, it's going to be looking something like this. It's hard to draw the chair conformation. So how I like to remember them, so if you're counting, like for instance here I'm counting counterclockwise, make sure you keep on counting counterclockwise so you still have the same direction of numbering. So my 1 is going to be right here, 2, 3, 4, 5, and then 6. So on carbon number 1, we know that the third butyl is pointing up. So in this case, it's going to be on the equatorial. Then hydrogen. And then on carbon number 2, we have a methyl that's pointing up. So in this case, it's going to be, instead of, see how it was here on the equatorial, now it's going to be on the axial, but it still points up. And then on carbon number 5, we have a methyl that's pointing up. In this case, it's going to be on the axial compared to before on the equatorial. So in this case, we're looking at one group on the equatorial, well, one big group on the equatorial compared to two small groups on the equatorial. We always choose the big group. The more stable one is having the big group on the equatorial, and that's why this will be the more stable one. Now for the other one, let me add another page here. So for the cyclohexane B, we're going to do the exact same thing. Right? Again, let's start by numbering the whole thing. It doesn't matter how you number this, just stay consistent. So 1, 2, 3, 4, 5, and then 6. We know that the first one is going to be pointing up. So if I'm drawing it here, it's going to be on the axial. So that's the third butyl. And then there is a hydrogen. On carbon number 2, it's going to be pointing up. So it's on the axial too. Oh, my bad. I meant this is going to be on the equatorial. And the hydrogen will be pointing down. Because remember, up axial and then up equatorial, up axial, up equatorial. So it's going to alternate always. On carbon number 3, there is nothing. On well, there is hydrogen, but there is no substituents. Number 4, there is nothing. Number 5, there is a methyl that's also pointing up. So on carbon number 5, right here, so we know here that the hydrogen is going to be pointing like that, and then this. So whatever here is pointing down is going to be axial. Here, whatever is going to be pointing up is going to be axial. So the CH3 is like that, and then you have a hydrogen. Now, if we flip this around, We're going to be looking at that. And then now we keep the same direction of numbering. So if it's clockwise, we keep going clockwise. So clockwise, we keep going clockwise. So actually, let's start numbering from here. 1, 2, 3, 4, 5, and then 6. So on number 1, the third butyl is going to be pointing up. So this means it's going to be, in this case, it's going to be on the equatorial. That's the hydrogen. On carbon number 2, the CH3 is going to be pointing up. So in this case, it's going to be on the axial compared to before on the equatorial. Carbon number 3, we only have hydrogen. Carbon number 4, we have only hydrogen. Carbon number 5, we have a methyl that's also pointing up. But in this case, it's going to be on the equatorial compared to before on the axial. So now looking at this, we have on this one, we have one methyl on the equatorial. But here we have one methyl, and then we have one tert butyl. They're both on the equatorial. So this tells us that this one is going to be the more stable one between the two. So you draw this one in your answer. Now let's go back. She's asking which isomer is more stable, A or B. So if we look at A right here, we only have the third butyl on the equatorial, as you can see right here. And then in this one, we have not only the third butyl on the equatorial, but we also have the methyl. So thus, the more, you guys have to remember, the more groups on the equatorial, the better, or the more stable. And also, guys, remember, this means there is less energy. And that's caused by having less steric hindrance around the 1,3 diaxial. So the answer will be here, B. Alright, so moving on. The iodination of the compound below gives the mixture of products. Provide a mechanism for the propagation step that leads to the products shown. So I'm gonna, on her key, she shows only the propagation. I'm gonna also show the initiation. So you're not required to, but it's good like info to know it. So for the initiation, what happens in the first step, the UV light, this is UV light. What's gonna happen is, it's gonna break the bond between the two iodine. And here you will notice that when I draw the arrows, they are one-sided arrows. And this one-sided arrows means that I'm only moving one electron, so one radical. Compared to before, when we used to draw the resonance, we'll used to take a lone pair and then move it and draw it as a double arrow like that. Make sure, well, you're not going to be drawing because it's going to be multiple choice. But if you were, that's an important thing to remember. So now with UV light, you're going to end up with two iodine radicals. Those radicals are not stable at all. Not stable at all. Right, so what that means is that they want to react. They want to react. Now moving into the propagation step. Propagation step. You have two steps for this one. So the first one, what's going to happen is the cyclopentane with the ethyl, CH2, CH3, is going to react with one of the iodine radicals. And what's going to happen here, this hydrogen and the iodine are going to react. So what's going to happen here, this is going to push a radical into the cyclopentane on this carbon right here, and this radical and the radical left for the hydrogen is going to react together. And what is it going to cause? It's going to cause forming an HI plus a cyclopentane with the cyclopentane with the ethyl, and there will be a radical on it. Now the second step of the propagation step, I just don't have space, so I'm going to just add all of that on a new page. So the next step of the propagation step, what's going to happen is this radical that we had just a second before it's not going to react with the other iodine radical. However, it's going to react with the I2, forming this thing. And now the cyclopentane will have an iodine, CH2, CH3 with an iodine, and then you're going to have an iodine radical. So that's pretty much the mechanism for this question. Now, if you notice something, if we go like at the end and like subtract the reactants from the products or product from reactants as we used to do in general chemistry, you'll notice that we had the radical iodine and the radical iodine, right? And then we had the radical cyclopentane with the ethyl, and those two will cancel out. And then the final reaction will be a CH2, CH3, H plus I2 will give us CH2, CH3 with an iodine. And that's pretty much it. So this is a quick way to remember. Oh, plus HI, my bad. So this is a quick way to make sure of your work that it's correct and you're not missing any step. It can be helpful. And yeah, that's pretty much for the mechanism. Nothing crazy yet. Later on the organic chemistry one, you're gonna have much crazier mechanism than these. So given the bond dissociation energy below, calculate the overall for the overall delta H for the reaction in the box provided. You must show your work in the box below to receive full credit. So when we're working with the bond dissociation energy, or when you want to calculate the delta H, you guys have to remember that delta H is going to be the bond dissociation energy by the reactants minus the bond dissociation energy in the products. So knowing that, we'll look at the reactants first. So looking at the reactants, we know that the first step what happened is that we lost this hydrogen right here, right? So this is a tertiary hydrogen. We lost this tertiary hydrogen and we formed the radical as one step of the propagation. So what you guys gotta do is you gotta scroll down and look at bonds to tertiary, and then you look at the hydrogen, and that's 91 kilocalories per mole. So 91 kilocalories per mole plus the other thing, this I2, the bond between them, as you remember, broke. So you also have to look for one of those. So if you scroll down, and this is the bond right here, so it's 36. So 91 plus 36 kilocalories per mole minus, so you got to look at the product now and what bonds were formed here. So if you look here, the first bond that got formed is this iodine. So it's a tertiary iodine, so you look at the bonds to tertiary carbons, but this time you'd look at this one with the iodine. So that's 50. So it's going to be 50 plus, we formed the HI bond. So that would be right here. So that's 71. So 50 plus, it's too big. I'll just fit it here. 50 plus 71. And then if you add all of this, you're not allowed to calculate on test, so you should be able to do this. This is pretty simple math. So it will be plus 6 kilocalories per mole. Now are the products or reactants favored at that equilibrium? So if we look at this right here, it says that it's a positive 6 kilocalories per mole. And if we look, what this tells us is that the bond dissociation energy of the reactants is bigger than the bond dissociation of the products, right? Knowing that, we know that the reactants are more favorites, right? So the equilibrium will be favored towards the reactants. And that's the answer. Reactants. So you don't have to remember like delta H positive means what, delta H negative means what. Just remember, if it's positive, this means that the reactants are more favored. So this tells us that there are more reactants in the solution than products. Alright, so now let's move on to the multiple choice that I gathered from the ACS booklet. So looking at the first question, it's asking us which of these four resin structure contributors the most to the overall picture of this molecule. So when you're looking at the stability of the resonance, you always want to try to have you have number one, delocalization of the charge. And what I mean by that is like having charges far away from each other, and also try to have a full octet, and also have the negative charge on the more electronegative and then the positive charge on the more electropositive atoms. So it's asking us here which of these four resin structure contributes the most to the overall picture of this molecule. So the first two choices that I can immediately eliminate are these two, B and D. And the reason to that is that B and D, they both don't have a full octet, as you can see here. So remember, the big rule is no octet. No octet means it's not stable. So now looking at A and C, we notice that on the first one we have a negative charge on the oxygen and the positive charge on the nitrogen. Compared to this one, we have a negative charge on the carbon and the positive charge on the nitrogen. Now, as I mentioned before, the electronegativity goes from the bottom left to the upper right. Right, so if I scroll down and look right here, so I still have the arrow. So as you can see, the oxygen is more electronegative than carbon, making it the more stable with the negative charge. So now, comparing these two, we notice that A is going to be more stable. And the positive charge also has to be on the more electropositive. And when I'm saying about electropositive, it's the opposite of electronegative, right? So electropositive will move to the left instead of to the right. Alright, so the second multiple choice, what is the order of acid strength from strongest to weakest acid? So in this example, what I like to do in the first step is remove the acidic hydrogen. So in one, or deprotonating it, I'm going to have O minus. 2 is going to be CF3. Actually, let me draw this out. So CF, F, and then F. CH2, C double bond O, O minus. For number 3, we have a C, F, 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 and then C double bond O, O minus. And then for the last one, we're going to have C, Cl, 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 C double bond O, O minus. So the first thing that you all guys notice is that there is resonance for all of them, right? Around this oxygen, right? This can resonate and it resonates up there, right? They all have that. So that this is not a way to compare them. The other way to compare them is if you see this one has hydrogen, but this one has fluorine. Same thing with this one. This one has fluorines and this one has chlorines. Now, the first thing that you guys have to know is when you have an electronegative atom, like even that it's far away from the negative charge, what it does, it causes the delocalization of the charge. So by induction, those fluorine those fluorine can distribute the charge better. So what I mean by that is, if I look at this, number one, the cloud would look something like this. The electron, the partial negative cloud around it, or the negative charge cloud, would look something like this around it. It will be like more this side, and then it will be small to this side. But if I look at it right here, it's going to be more distributed among them. So this means there is a better delocalization of the charge, and this delocalization of the charge is what makes it super stable. So out of the bat, we can tell that number one is going to be the least stable one, because it's not the charge is not as delocalized as the other one, like 2, 3, and 4, that have a that have a electronegative next to it that can pull electron by induction. So immediately we know that this one, and this one are correct, while A is incorrect. And here they're trying to trick you, because some people will number them wrong, right? Because some people confuse between the small and the big sign. But you should always look at the question again. So what is the order of acid strength from strongest acid to weakest acid? So they're saying is that this is going to be the weakest acid. Now, comparing 2, 3, and 4, we notice that 3, as you can look at number 3, what's the difference between all of them, right? If you look at number 3, the carbon that has the atoms that are inducting the electrons is right next to the oxygen, so it's closer to the negative charge compared to number 2. So 3 and 4 have the same thing. Now, you should know that the inductive effect decreases a lot with distance. So the farther away, the less the inductive effect. So now, knowing that, we need to compare number 3 to number 4. We have a chlorine and a fluorine. So to be able to compare that, we have to look at the periodic table. So if we scroll down and look at the periodic table and compare fluorine to chlorine, we know that fluorine is more electronegative. And if it's more electronegative, means it's more stable, means there is more delocalization of the charge, meaning that 3 is going to be more stable than 4. So we know that 1 is going to be the most stable, 3 is 1 is the least stable, and 3 is going to be the most stable. So with that, we'll get rid of option D. We're looking at option B and option C. So now that we're looking at option C and B, we still have 2 and 4 to compare. Remember what I said before is, that the inductive effect decreases a lot with distance. So as I move far away, it's going to decrease the inductive effect. Even though the fluorine is more electronegative and can pull electrons towards it better, the chlorine is closer to that negative cloud, making it the better distribution of the negative charge, making it the more stable. So that's why B will not be the option and C will be the correct option. So that CH2 right here makes this whole thing be less stable, right? Because it's further away from the negative cloud. Moving on to the next multiple choice question, it's what is the correct IUPAC name of this compound? So when we went over the nomenclature, that's why I think the old tests for Dr. Bean are really good practice, even though it's not going to be the exact same, it's going to be multiple choice. But I think this way, like what we learned before while solving it by hand, is you learn the concept down. So when you're looking at this question, it's going to be easier to answer. So first step, as I mentioned before, we have to find the longest chain. So let's start counting. 1, 2, 3, 4, 5, 6, 7, and then 8. This is the longest chain. I don't think there's anything longer than that, so that will be the longest chain. But now we also have to decide if we start counting from this carbon or this carbon. So if we start counting from this carbon, 1, 2, 3, 4, 5, 6, 7, and then 8. So if we look at the orange, the substituents are going to be on carbon number 2, and 2 on carbon number 7, so it's going to be 277. But if we look at the orange, we'll have 227. And as I mentioned before, you always look at the first point of difference. So 2, 2 matches. I look at the second one, 7, 2. This one wins automatically. I stopped looking at further that. The first point of difference. So it's going to be 227. I mean, from now on, it's pretty easy because there's only one with 227, trimethyl octane. But I'm going to just keep going. So you have trimethyl here. 1, 2, and then 3. And then the octane, because it has 8 carbon, it's octane. And that's pretty much it. The other ones are wrong. Like this one is saying tert-butyl, but they're taking butane as the main chain, right? So that's immediately wrong because they're not taking the longest chain. This one is saying it's a 1 tert-butyl. This is not even correct because it has an octane, but it also has a tert-butyl. So that's also automatically wrong. And this one also doesn't have the longest carbon chain. So that makes it wrong. And this one makes it wrong too. So which Newman projection represents the most stable conformation of CH3 taken twice, CH3 2 times? So what I like doing for these problems is just drawing it out, and then you can see where they're looking at. So CH. So there's a hydrogen, a CH3, and then there's a hydrogen, and then another CH3. So that's the compound what we're looking at. And remember, when we're looking at Newman projection, we're looking at this from this angle. So now we're looking at it laid down on the table. But when we're doing Newman projection, we're looking from the side angle. So knowing that this carbon right here represents the front carbon, and the circle on the back represent the back carbon. Right, so like let's change colors. So that this carbon would represent this one, and the orange one would represent the back one. It's all relative, right? So it doesn't matter which one's going to come first. It depends how you're looking at it. So you're either looking at it from A or you're looking at it from B. That just depends. All right, so let's look at the first one. Looking at the first one, it's connected to 2 CH3s. That's correct. My bad. It's connected to 2 CH3s, and then the back one is also connected to CH3s. But if we look at this one, it's all the methyls are next to each other, which makes it unstable. We're gonna try to find something more stable than that, because remember when I explained Newman projection before, when you have methyls next to each other, there is steric hindrance, which makes it not stable at all. But they're asking for the more stable one. For C, the front one is connected to CH2 methyls, and the back one is also connected to 2 methyls. This time it's better. There's a methyl next to a hydrogen, methyl next to a methyl, and then a methyl next to a methyl. So there is less steric hindrance than A. So now let's keep looking, see if we can find something even better, right? So looking at this one, this is the front carbon. It's connected to a CH3, H, and H. Well, this is not the same molecule, right? Because if you look at this one here, this one has a CH3 and a CH3, right? But this one here, it's saying that it only has one CH3, so that's automatically wrong. This is a different structural isomer, right? This is like, so what they're having, and if I want to draw B out, I'm gonna have something looking like this: C, CH3, C, CH3, 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 a hydrogen, and a hydrogen. So you see, this is just a different form, different molecular structure. So it's a structural isomer. So that's automatically wrong. So now looking at D, it says that the C in the front, which is also the same case, has a 3 CH3s, and the back one has 1 methyl. So that's also automatically wrong, making my only option is C. So now, what are the respective hybridization of the atom number 1 to 4 in this compound? So as I mentioned before, how I like to do this is I like to calculate or get the total number of atom connected plus the lone pairs. So if I look at the nitrogen, it's connected to 1, 2, 3 plus 1, so that's 4. So that means this is sp3 hybridized. So now this is wrong immediately. So I only have between these two choices. Looking at this carbon right here, it's connected to 1, 2, 3. So this one is sp2. So the only two choices still are C and D. Looking at the third one, it has 1. Well, this CH2 is like H and H, right? So it's 1, 2, 3, and then 4. So that's sp3 hybridized. So it's this one. Just to make sure of my final work, I'm going to look at the carbon number 4. It's connected to 2, and it's sp hybridized. Well, I can't tell, but I know that this is going to be wrong, so it's going to be D. So, like, I think multiple choice can be easier. It depends what you're doing. Like, if you're actually solving, like, nomenclature, it will be better to, like, actually write it down because you can get partial credit. But now it's hard because you cannot get partial credit. But at the same time, some questions are much more easier than actually having to, like, answer something, right? So on the last multiple choice question that I have for today, it's going to be which Newman projection represent the most stable conformation for 3-methyl pentane when viewed down the 2,3 carbon-carbon bond. So let's draw this out. CH3. So carbon 2 and carbon 3. So what I do usually is 1, 2, 3, 4, 5. So I take carbon number 2 and carbon number 3. I draw all the atoms attached to it. So I'll have carbon number 2 as 1 hydrogen and then 1 hydrogen. And then on carbon number 3, I have a methyl. Carbon number 4, I have a CH2 and then a CH3. So we're looking at this carbon, and we're looking down from them, right? We're looking from this angle. We're seeing what is attached to. So first of all, you want them, remember, when we're looking at the most stable conformation, we're looking for the one that are further apart, so there is no steric hindrance. So let's look at A. So this is, well, if you look at this one is connected to a methyl and 2 hydrogen. So this one is represented by this carbon right here. And the back carbon is connected to an ethyl, which is right here. And it's connected to a CH3 and connected to a hydrogen, which it is, and I didn't draw here. But if we look here, we have the CH2, CH3 not next to any methyl, which is really good, but the 2 methyls are next to each other, which is better than having an ethyl next to a methyl, right? Now let's look at this one. Also, I don't know how she's gonna have the questions, but for ACS they always like have tricks where like, oh yeah, like you're like just looking which one is next to each one, and then you're gonna get confused because sometimes they just give you the wrong molecule. But I don't know how she's gonna do it on her test, but this is what I noticed when I took the ACS test. That's why I keep on counting and looking for the carbons, right? So I don't know if this one has something like that, but we'll see. So this carbon is gonna be this one because it's connected to a hydrogen and a hydrogen, and it's connected to a methyl. And the back one is connected to an ethyl right here, and they connect to a methyl. Now this one is less stable because there's an ethyl next to a methyl. So ethyl next to a methyl compared to an ethyl next to 2 hydrogen and 2 methyl to next to each other. As of right now, A is the most stable one. So how I explain to like my workshop students is when you're looking at this, look at it as like you're at the movie theater, and then when you're going to sit down, would you rather sit next to a big guy or a small guy? So like here, the methyl would rather sit next to another methyl compared to sitting next to an ethyl, right? Because ethyl is a bigger guy, so like you don't have much space on your seat. Now looking at a B, we know that this one is connected to its methyl at 2 hydrogens. So it's this one. And then in the back side, it's connected to a methyl, an ethyl, and the hydrogen, which is correct. But now this one, I think as of right now, this one is the least stable because you have methyl next to a methyl next to an ethyl. So as of right now, this one is the least stable. And then for the final question, for the final option, we have this carbon connected to 2 methyls. See what I'm saying? That you have to look at each one. So look at this one. This one is connected to 2 methyls. And then in the back side, it's connected to an ethyl and a methyl. So that is just a completely different structure. So if you want to draw this one out, it's going to be C and a carbon. The front one is going to be connected to a CH3, and a hydrogen. And the back carbon is going to be connected to a CH3, and the CH2, CH3, and the hydrogen. So these two are completely different molecules, right? So just be aware that she can trick you like that. And like for this instant, if you're just going fast and you're like, oh, those are next to each other, this is not stable, you won't notice it. But if she gives you something like there's a hydrogen here and the hydrogen here, you might be like, you might choose D because, oh, this one's the least stable, but it's actually different molecules. So just make sure that the molecule is the correct structure. So yeah, and that's where we're gonna be stopping at. Good luck everyone on the test. I hope all of you guys do well on the test, and yeah, good luck.